All right, so again, sorry for the delay, but I'm hoping that you were able to watch the lecture that I uploaded in place of, we had some technical difficulties last week. And if you did sort of, go through that lecture, the main point of this module, which I wanted to really convey, was the following, that a lot of these models required for perception, planning, and control for self-driving and autonomy, they are data-driven models. And in particular, one very popular choice of these data-driven models is using artificial neural networks, or in particular, convolution neural networks. So the first lecture, which now is just a video online, walks you through, how you would go about using the network, and the rest of the module, the chosen sort of application focus is designing one such example of a neural network, right? We can't design a network to solve all the problems of perception, planning, and control. So we will pick a problem of perception, and in particular of lane detection or vehicle detection, and we learn how do you design a data-driven convolution neural network to do that task. And so, one of the things in the previous lecture, when I conclude, is that why do we need a data-driven model? And the key point was that traditionally you would have feature engineers, right? So human engineers who would try to describe what a car could look like or what lanes look like, and you would use sort of the principles of canonical computer vision, in which you are trying to find a particular template in an image, for instance. And all of this was very hand-driven until a few years ago. We had the ability that you don't have to design these features yourself, right? Because you could always ask that, why are you choosing a particular feature versus something else? A lot of this human effort was required, and this was the limitation. And I do sort of talk about ImageNet in that lecture online. And so the idea was that, can we actually get rid of this human element and just learn these features or representation altogether? And this is actually what motivates us to do the self-driving task, where, as shown in an example here, well, nothing is working today. Okay, great. So as shown as an example here is that we have data of when a human is driving. You can at least see the cursor. So the human is driving, and while that human is driving, we are always logging the images from the camera, for instance, and his or her steering and acceleration inputs as well. So if we have this for every image, we have the corresponding sort of steering or the human input of acceleration. And then the idea was that you want to train a network or a convolution neural network that will learn how to automatically drive itself, right? So this is sort of where we want to be, that given some images or data or examples of human driving situations, can we actually learn a controller in this case that will just look at the pixels of the image that is coming in at every, once every thousands of times every second, and for each one of them, or for a history of them, generate what should be the steering angle in the world. So in particular, this is what is called behavioral cloning, and you have, a convolution neural network can do behavioral cloning. So just like how we have done so in the previous modules, I will first give you a very toy example, or just a very high-level intuition for what is even a neural network. And I know most of you have maybe already seen this, so we can pace ourselves accordingly. But I want to give you a very simple toy example of building your intuition for why a neural network does what it does. And we are just talking about a regular neural network. And then hopefully we have the time today to also motivate why you need a convolution neural network. And so that's really my intention in the lecture today, and maybe in the next lecture, to just go into the intuition first, and then we will look at code and math. Because I want you to have like a code base where you can train your own neural network as well at the end of the day. Okay, so with that as our high-level motivation, that we want to build and train these neural networks for driving or some part of the driving task, let's jump into what is a neural network, how it works, and let's look at a very simple, the simplest possible, or a toy example of how to build a neural network. So this is not at all a mathematical, rigorous sort of overview. It's mostly to build intuition and introduce some terminology that you may be, for some of you, you are looking at that for the first time. If you already know how neural networks work, then this is just a refresher for you. All right, so our example is the following. We have a very simple image. It's a 2 by 2 pixel image, not even 2 by 2 megapixels, which is usually considered nowadays a small image size. This is literally 4 pixels. And this is our input image, and what we want is we want to categorize the pattern that these pixels make into these 4 categories, right? So either you can have a full solid, it could even be all black, or not, it doesn't have to be all white pixels, or there's a vertical pattern, or there's a diagonal pattern, so on and so forth, or there's a horizontal pattern. So traditionally, when people teach neural networks, they go into biology and the history of how this field came about. And all that is interesting, but I'm not going to even touch that today, right? So don't worry about why it's called a neuron right now. I'll tell you later why all of this has some analogy in biological systems as well. But you don't need to be familiar with biological neurons to understand a neural network. They're actually very disjoint in some sense. So let's build a network that will accomplish this task of, given a 2 by 2 pixel image, we want to classify the pattern in that image. That's the problem. This is actually a very simple toy version of, given a video, I want to figure out where the vehicle is in that video. Or given a video, I want to classify or figure out where the lanes are, and things like that. So let's build that intuition first. So first what you do is, probably the simplest thing to do is that you take your 4 pixels and you can map them into what you can call input neurons. It doesn't even matter that they are called input neurons. We are just literally taking every pixel and considering that as an input to our neural network. And these pixels could be on a scale. It could be like a gray scale, which goes from -1, which corresponds to all black value, and +1, which corresponds to an entire white pixel. And it can take some discrete or any intermediate value, right? So given some image, as an example shown here, the values of our input neurons are simply the values of the pixel corresponding to this mapping that we have hard-coded into our system. Okay, so the top neuron gets this top left corner value, and so on and so forth. And our input neurons are not doing anything interesting. They are simply like reading the image, if you can call it. And this process is many times called flattening your image, because you have a 2D matrix, which is your image, and you are flattening that out into a single vector. Already, though, we can do something very interesting, right? So if you look at each of these neurons, what I have drawn is sometimes called the receptive field of the neuron itself. So what does receptive field mean? It means that what is the input image such that my neuron can obtain its highest possible value. Okay, so let me repeat that. In our spectrum, the highest possible value any pixel can take is +1, because it goes from negative to +1. So drawn here is just an interpretation. This is not some mathematical encoding. We are just interpreting what these neurons are trying to accomplish. And what I hypothesize or assert is that corresponding to every neuron shown here, which is simply a reader of our input, we can already think of what is called a receptive field, such that, so for instance, this neuron right here, it can get its highest possible value when the top left pixel is +1. And it is agnostic to the other pixels, which is why we have this sort of checkered board pattern. This is my way of saying we don't care about the other pixels. So on and so forth. For every neuron, you can say that they have a receptive field corresponding to which pixel they were reading. So nothing special has happened. So in a neural network, what we want to do is we want to do this classification task, we are going to increase the complexity of these receptive fields. That's one way to think about what a neural network is doing. In other words, stated the same thing, every sort of layer of the neural network, and I'll describe what a layer does, is going to learn some more complicated pattern. Pattern meaning, in the image scenario, it's very clear what a pattern is, but in general, our input could have been some time series of temperature history, and you could still have patterns in there that you could learn. So what's the next step? One next step is we look at the values of the inputs, and we have a weighted sum of all these values. So I've drawn some edges to denote this weighted sum. For example, if all your weights are just the same, uniform weight, each of them is equal to 1, your weighted sum would be 0.5 in this example. But that's not always the case. Sometimes, or more likely the case that your weights are all over the place. And these weights are allowing the neural network to look at all these pixels and establish relationships between them. That's why you have some weighted addition. So, obviously if you have, your weights can be negative or positive, and that will lead to a different weighted sum. This is pretty obvious. So in my notation from this point onwards, whenever we have a negative weight, I'm going to denote that edge with a black line. And if we have a positive weight, I'm going to use a white line. And not only that, going on from this point onwards, the actual width of the line or the thickness of the line would give you some idea of which has a higher weight, whether positive or negative. Okay, so we weight the neurons, have a weighted sum of all our input neurons in this case. And the next step we do is we look at this sum and then we pass it through a nonlinear function. And this nonlinear function in this example is nothing but a sigmoid function. Now you may be thinking, why are you doing all of this? And I'll tell you why. Right? The idea is that this network or the sequence of neurons, they have to be able to capture some nonlinear behavior of my input. Right? So if you go back to actually the very first module, our data or the relationships of the data with the inputs of the things which govern the temperature of a building, it was a nonlinear relationship, but we linearized it to a simple form by making assumptions. So most of data in nature or in images, the patterns in images, it's highly nonlinear. You can't have, I'm going to say a statement, and if you have taken a machine learning course, it will be very clear. Our data is usually not linearly separable. Right? So we have 4 categories, and we want to classify solid, horizontal, diagonal, vertical. If they were linearly separable data, we wouldn't be needing nonlinear functions within our network. But usually that's not the case. And that's why we need our collective neural network to capture that nonlinearity. And that's one of the reasons why we need a nonlinear function. So just to recap and go back to this example, we take the sum, which is the weighted sum from the previous input layer, and we look at, well, what is the output when we pass it through a sigmoid function? And so you can think of the sigmoid as it will always, no matter what the input is, it will always produce an output between -1 and 1 in this example, because of the way the sigmoid function is defined. Okay, so we can keep doing this for whatever weights or weighted sum we get, and it will always produce an output between -1 and 1. In fact, the further larger your input is, the closer you get to +1 in this case, and vice versa. So to go back to our example, what we have done is we had some inputs, we mapped them to our input pixels or input neurons, we calculated some weighted sum, and then we passed that sum through a sigmoid function. And what we get is, in this example, this value which is almost 0.75. Yes?
So you have some questions, might be like...
Yeah, go ahead. No?
Set this 0.5 or 0.1.
Very good. So I'm glad you asked. And the obvious question is that who is the oracle which has told me what these weights are? And the answer is that this is the part of the training of the model that I will explain later. So I'm just showing you how the network works given some weights. I haven't yet explained where these weights come from. And in fact, that's the whole process of training, as some of you may know. Yeah?
Also, how did you normalize somehow from the 1.075 to 1.7?
This is this process. So the input on the x-axis was 1 point whatever, the sum. And then we look at the output of the sigmoid on the y-axis.
Wait, is this sigmoid function like always the same, or can you have like a steeper curve? Is that part of it between?
The sigmoid is a standard function that this is the shape of that function. This is the slope, roughly speaking. It will always take the input on the x-axis, so y equals sigmoid of x. And it will produce an output where it will always lie between -1 and 1. That's the property of the sigmoid. Another similar function is the tan h function, right? It also has a different slope, but essentially does the same thing. So that's where the normalization is coming from. So as a result of actually this normalization, now here's another insight for this example. The output of my sigmoid layer or this is not a layer yet, it's a single neuron. So this value actually will always be between -1 and 1, correct? And that property is also true for my input pixels, right? Every pixel will always be between -1 and 1 to begin with. That's sort of the, the layout of this problem. So actually, I can treat this as another virtual pixel in some sense. Okay, so whatever I did when I took the weighted sum and passed it through the sigmoid, I can do this again with 0.746 as the input. In fact, not only there was nothing special about this neuron right here, right? So this neuron is kind of very selectively choosing which one of the input neurons to sum together. You can actually do this for all possible combinations of the input neurons. So now what you see is another layer. In fact, there is no reason why this layer only had to be 4 neurons. There could be 400, it could be 4 million. That's like a design choice. But what is important is each of these neurons is summing together some value of the inputs, a weighted sum, and the weight depends upon, in this case, the selection of these edges. And the output is squashed due to the sigmoid function. Now, to keep things simple, again, I'm not trying to explain very rigorously what is happening mathematically, but to keep things very interpretable rather, I'm also making another assumption here from this point onwards, which is stated on the right-hand side, that for now onwards, I will always show you the weight as either being 1, 0, or -1. In reality, we have seen the weights can take whatever value, and we'll actually see why that is the case. But for this example, and especially to study the receptive fields of the neural network, we will just assume that whenever there's a white edge, it's +1 weight. Whenever there's a missing edge, there's a 0 weight, and if it is a black edge, it's a -1 weight. It's just a simplifying assumption. So with that in mind, I'm just showing you an example of what this layer, second layer, could look like, which is taking some combination of the inputs and combining them and passing them through some sigmoid function. So let's look at what has happened in the receptive field view of this network. So if we look at, say, the top network or the top neuron of the second layer, this is multiplying the input or the receptive field of this neuron by a +1, and also multiplying by +1 this bottom neuron of the previous network. And therefore, its receptive field has grown to this sort of vertical white column on the left. And this is sort of arbitrary, but this is consistent with at least the lines drawn and the color of those lines. So already with this idea of summing together, taking a weighted sum and passing it through this sigmoid function or nonlinear function, we have a much more complex receptive field. Right? A network has already started. So this neuron will take a maximum value if the input image was exactly this. Is everybody on board with that statement, right? So you could keep doing this, right? The other thing we noticed was that the value of the output of the sigmoid layer will always be between -1 and 1. So functionally, there is no difference between the values of the output at this layer and the values of the output of our sort of input layer, because they were also between -1 and 1. So I can just repeat this as many times as I want. Well, why would I repeat it? In this example, the sort of reason why you would want to repeat or add more layers is you want to have much more richer receptive fields. Because we have seen by combining the inputs from the previous layer and passing them through this nonlinear function, we can get more complicated patterns as the receptive field of our neurons. Questions so far? I know this was pretty rapid fire, but let me know if you have any questions. Okay, so this is just the machinery. There's many, many more questions. Why four neurons in this layer? Why 2 layers? Where are the weights coming from? All those are legitimate questions that we'll answer. So let's see this example through. Now I can say, but the same logic in my simplified view where edges are just -1, +1, or 0. In fact, I'm not even showing the 0 edges. Now you can see in my second sort of layer of the or in the third layer in this picture, the receptive fields have become even more complicated. In fact, it's after passing through 3 layers that I can actually look at all 4 pixels. So far we've seen sort of 2 canonical properties of a neural network. We have seen weighted sums and we've seen this nonlinear function, and we are just sort of combining all of those. There's one more trick or one more mathematical function which is very commonly done, and that is what is called another nonlinear function, which is called a ReLU, or a rectified linear unit, right? So just like sigmoid was a nonlinear function, I can also take the input from my previous weighted sum, pass it through this function. So what is a ReLU? A ReLU is nothing, but it says if your input is negative, my output is 0. And if your input was positive, then my output would be the same as the input. So this is like a constant slope 1 function. Right? So it behaves like a rectifier where it's just killing everything which is negative. That's why it's called a rectifying linear unit. So look at this picture now where we have added for each of the neurons which were in this third layer, I have added ReLU functions corresponding to a different edge. Okay, so let's look at this first one to make sure everybody's on board. So here, the receptive field of this neuron was all 4 pixels are white. That's when it will get its highest possible value. Now, if you multiply that with a +1, nothing changes. A ReLU will just output the same field. But if you multiply the same thing by -1, if your input image was all black pixels, then this neuron will take the maximum possible value. Because it's ultimately getting multiplied by -1, which will mean that the ReLU will get a value of sort of all 1s. So, yeah?
So, last one, I think the one that we flagged out, that's black on the top and then white on the board, so your negative weights.
No. So, I think you're misinterpreting what this is telling you.
The third column, not this column. This is the fourth column. The previous one, the bottom one.
So, you are talking about this neuron?
The very last one, yeah. It's black and white. That's plain.
Okay, let's see. So, this has a receptive field of top left white and black. So, if you multiply that by -1, you would get, yeah, you're right. I think this should be black and this should be white.
Eventually, that's the same thing.
Yeah, no, but that's a good observation, sure. So the observation was that, if you look at, oops, not this. If you look at this neuron right here, the bottommost one, its input is, we are multiplying by -1 the previous input of the neurons in the bottom part of the network. So if the receptive field of this neuron was, let's say, +1, -1, and then we don't care. If you multiply that by a -1, it should be the opposite of this. So that's a valid point. And you are right, it won't affect eventually what I want to show. But is the effect of ReLU clear? Okay, it might not be clear why I added ReLUs here, but is the effect clear? And I'll promise you, I'll make sure you have answers to all of the whys as well. So finally, we have, in this simple toy example, we can visually see that after this ReLU operation, we are kind of, we have rich enough receptive fields that we can now start to make or start to think about a classification. But that's only possible because we can visualize these fields very easily. So the only thing that remains to be done is have some more edges and have another output layer where the value of the output neuron would be maximum based on how it has, captured the inputs from the previous layer. So how does this actually work when we get an image? Let's look at an example and then you'll understand it better. So here's an example. Let's say this is my input image. Okay, I've already kind of hand-wavily explained what the architecture of the neural network is. Right now, what needs to be clear is what is the function of each of these neurons. What is the sigmoid doing? What are the edges doing? And what is ReLU doing? How did we come up with this is a separate question altogether. But let's just say, given this network, how does it actually classify? So if this is my input image, after my first layer, I will just read those values into my first layer, right? So I'm just reading -1, -1, +1, +1 into this layer, which is just the definition of the input layer. For the next layer, you can see each of these neurons is going to combine the value -1 or +1 in some manner, which is based on the color of the edges, and pass that through a sigmoid function. So let's actually do this top one first. So this has a -1, and you will add to that a +1 multiplied by +1 because the edge is white. So here, the weighted sum is going to be -1 plus +1. It's going to be 0. And so when you pass that through a sigmoid, the answer will be 0 as well. So you can convince yourself that once we do that for all the second layer, we will have two neurons where essentially they are out of play because their resulting weighted sum was 0. It doesn't even make sense what happens after you pass them through the sigmoid. And the bottom neurons are going to take this value in this case. So you can keep repeating that. In this layer, you will again multiply. So 0 multiplied by something is 0. And then actually the color of this edge doesn't matter. We already know that this neuron will also take a value of 0 for this example. So the only interesting stuff is happening here. And this is what you end up with. After the third layer, only one of the neurons has some value, and all the others are going to be set to 0. And why are they getting set to 0? Because of the way these edges have been designed in this example. So ultimately, if you have this image, the ReLU will make sure that, I know these are flipped right now, but for this picture, the input was white on the bottom, black on the top, horizontal. And you can convince yourself that with the ReLU operation, this will be the only network which takes a positive value, or only neuron, not a network, which takes the positive value. And so we can then say that our network has actually classified this as a horizontal pattern image. So what did we do? Just to recap, we understood what a neuron does. It does a very basic operation of combining previous layer outputs with a weighted sum, where the weights in general are anything. In this toy example, I deliberately chose them to be -1 or 1 or 0. Once we sum the weights together, we pass the result through a nonlinear function. One example of that nonlinear function is sigmoid. Another example is ReLU. You can do anything. And ultimately, when you stack these layers together, the motivation or sort of the reasoning behind layering them in the first place is you can think of the receptive fields becoming more complicated. Otherwise, it's just haywire, right? There's no rhyme or reason why you would layer one versus the other. There has to be some motivation behind stacking layers together. And one of them in this example is very clearly illustrated is you want deeper layers to have more complex receptive fields. So they will get activated when complicated patterns exist in the input. Possibly, yeah. If you change the ordering of the layers or the type of layer, you can build an entire network which has no sigmoid, only ReLUs. You can have a different sort of desired result. So now let's answer one of the questions, which is who gave you these weights? And my first argument is you already know the answer. We've sort of seen that entire thing happen in our first module. So what is this? This is nothing but a model. And the parameters of this model are the weights. In fact, there's another thing called a bias, which I haven't shown, but don't worry about it. the parameters, the only thing unknown about this model is, the subtext is, given that you have decided there's going to be 4 neurons in intermediate layers, given that you have decided what is sigmoid, what is ReLU, once you know the architecture, or once you know this, the fully connected graph, the only unknown is what are the weights of these edges. Everybody agrees with that? There's nothing else which is unknown. Sure, there's a question of how did you choose all of that set of things at which layer, how many neurons. But once you have made that choice, once you know the hyperparameters of this model, the only thing unknown are the weights. And so if we have a model and it has some unknown weights, we have already seen a machinery to estimate the best weights which can describe my data. This is all of what you did in module 1, actually. So we looked at gradient descent and many, many other variants of gradient descent. A similar principle applies here, right? So in reality, in my toy example, this was my input, and then some human has given me a label, the ground truth. The ground truth was that this is a horizontal pattern. That's why the value of each of the corresponding labels is 0 and horizontal is 1. And although I simplified the previous neural network to always have weights between -1, 0, and 1, in reality, the weights could be anything. Sort of what we saw as an intermediate example when it was some -2 or 0.5 or whatever. So it will actually very unlikely be the case that my network exactly produces horizontal as the output. That was only in this special example. For a generic neural network, your outputs might look more like some sort of aggregated sums from the previous layer. In fact, I can already say that there's an error in this slide because my last layer was ReLU, and the ReLU can never output kind of non-negative. But I did have some weights, so it is still possible. Point is that if your weights were really, truly allowed to be anything that you want, then what you would get in the output layer are some scores, right? So you have some scores corresponding to what is the sum of what is the weighted sum into this output layer, where this weighted sum is calculated from the previous layer's output. So if you have this as your, let's say, prediction or your score, and you know the ground truth of your actual image, you can calculate the error. Right? So you are predicting a score of 0.5 for solid, but in reality the score is 0, so you have an error of 0.5. And so you can do that for all possible outputs in this very simple network. And so no points for guessing what happens next. We sum up the error, or we can take the sum of square of the errors. Or you can use whatever least square errors, your favorite function of your error estimation. So once we have the total error, now what we want to do is we want to go back and adjust the weights of the edges of our network such that we want to minimize the error. It's exactly what you have been doing in your first module, where you have some error between what you predict from your state space model back then, and you use that to use gradient descent to figure out how to move in this space of parameters of your model. Only thing which has changed is the parameter space right now is the weights of the network. And there's one more thing which is tricky about this, that if you think of your network as a function, it has some nonlinear compositions of some nonlinear functions like ReLUs and sigmoids. So the question will just be, how do you take the gradient of this complicated function where you are adding inputs and passing them through some nonlinear small functions. Okay, but if you visualize, this is my sort of the x-axis is a simplified picture. This is my dimension of the weights of the network. Y-axis is the error, and so if you based on the gradient of this error function, you can figure out in which direction to update the weights. All right, so we've already seen this, so I'm not gonna, and we've already seen this problem as well, that in reality, that gradient descent is actually this multi-dimensional problem where you have a lot of peaks and valleys. In fact, one of the examples was to use this multi-start search to figure out a better sort of initial guess so that you can, eventually you want to find the globally minimum of this highly nonlinear function. So think of this peaks and valleys as your error function in some parameter space, and you want to start from some initial random guess, and then figure out what is the minimum of this function. So we already know that to do that, we need the gradient of the error with respect to the weights, right? So what the quantity we need is, how does the error, remember, is only calculated at the very last output layer. But what we want to adjust is even the weights at the first layer itself, right? So here is where the problem is, that you want to be able to calculate that slope of the change in error to the change in weight for all the weights of your network, no matter which layer they were in. And so to do that, we will use some very clever properties in calculus. I'm sure you would have already seen them, but I will still show you how that happens. But before we do that, let me pause again if you have questions, right? So what we are trying to now do is, given that we have calculated the error, let's say it's least square error, can you now calculate the derivative of that error with respect to every weight of the network? That's the setting. Is it clear? Okay, so let's see how do we navigate that problem. So the first thing we will exploit is chain rule in calculus. Okay, everybody would recall chain rule, but here is an example of, say, one path which goes from my input, which say is this neuron right here, all the way through different layers where I can calculate the error. Okay, this is just a sort of a representation of one such path which goes through everything. The first thing we want to do, like I said, is you want to calculate this quantity. You want to calculate how would the error at the output change if I change one of the weights, let's say at the very beginning, ever so slightly. That's what a gradient is, right? How would the output change for every unit change in, say, the input? But the problem is that between this weight physically being present as one of the layers, there's many other things which are going on in the network before you reach the output where the error is produced. There could be things like sigmoids or sum or ReLUs. So each of these edges or each of these neurons could be doing some nonlinear function. So how do we compute the rate of change of the error at the output with respect to any one of these intermediate weights? In this case, I'm showing you the extreme version where I want to compute the derivative with respect to the very first weight. But you could repeat it for any of the intermediate weights as well. And what allows us to do that is expressing this quantity that we want to compute in this chain rule notation, where I can say the rate of change of error with respect to the weight is the rate of change of this output A with respect to the weight, multiplied by the rate of change of B with respect to A, C with B, so on and so forth, until you get to the very last layer, which is the rate of change of error with respect to Z. Okay, so this is just an algebraic manipulation of expanding out this error function that I want to calculate as a product of these intermediate gradients. Yeah. Yeah. Why do you say they have to be independent? But for this chain rule, it doesn't matter whether they are independent or not, because I'm just simply expanding this expression as a product of all of these gradients. So right, I don't have to walk you through this, but delta B eventually is getting canceled out. So they are just equivalent expressions. So really what you want to do is, you start from your error and you look at how the error would change with respect to just the preceding output. So that quantity would be delta error by delta Z. If you know that, you can then compute how would Z change with respect to Y, and just multiply that with that. And you keep on back propagating this gradient all the way until you eventually will get to the point where you just need the rate of change of the output at A with respect to the weight. And so this is the very simple toy picture representation of what backpropagation is. Backpropagation is what allows us to look at the error and the output and propagate it through the layers of the network all the way to the weight which we want to adjust. We still haven't solved all our problems. This is just the high-level idea. The low-level problems are that if y is some x times, or y is the sigmoid of some weight times x, there are all these nonlinear relationships between intermediate layers. So when you backpropagate, how do you actually take the derivative of those nonlinear functions? In other words, let's look at a very simple picture. This is just one arbitrary piece from that chain. And the simplest possible case is that I want to compute the rate of change of error with respect to A, where I know what is the rate of change of error with respect to B. So I know this quantity because of the previous chain link. So the simplest case is that B was just some weighted average of A. And if that was the case, then you know that delta B by delta A is nothing but W. Okay, so it's like the most straightforward case that if your output B was just a weight multiplied by the input A, then if you know the error at B, or the rate of change of error with respect to B, the rate of change of error with respect to A would just be the same multiplier. That's what this is saying. Questions? Just stare at this for some time, because I think I'm going a bit fast, so let me slow down. Is it clear what I'm trying to show here? That one possibility in this chain is that your next layer was some multiplier times your previous layer. And if that's the case, then the error can be just propagated by multiplying with a constant, in this case, the same weight. Another possibility is that the next layer were actually a sum of previous layers. And in this case, let's say we know what the error was with respect to z, so we know this term, delta error by delta z, and we want to compute delta error by delta A. So in this case, assuming that the initial value of the weights was 1, you would have z is just a sum of all these inputs. So in this picture, delta error by delta A would be nothing but 1 times the previous error. Why 1? Because I'm still sticking to all of these white lines are 1. Okay. In reality, this could be W1 times A plus W2 times B, then this would just become the corresponding coefficient of A. And this intuitively also makes sense. When you take a weighted sum and then you ask, if I were to change one of the elements of your sum by 1, how would the output change? It would be weight times 1. And that's what this is saying. The problem is when B is a nonlinear function of the input, like sigmoid. So there can be a case where you know what was the rate of change of error with respect to B, and you want to find out the rate of change of error with respect to A, but the relationship between B and A is not that constant multiplier, it's not a summation, it's this nonlinear function on the top right, which is the sigmoid function. So now you need to evaluate this expression, delta B by delta A, to figure out how would this error backpropagate from B to A. Correct? And so to do that, we can donate this function by sigmoid or sigma of A. And can someone tell me what's the derivative of sigmoid, if you have seen this before? Okay, so let me tell you. Excellent. Right? So sigmoid has a special convenient property that the rate of change with respect to the argument is the function itself multiplied by 1 minus the value of the function. So if you take the derivative of this expression with respect to A using calculus, this is what you will end up with. So point being that even when B was a nonlinear function of A, and we know the error at B, we can compute the error at A by just multiplying it by this quantity. So it still falls in this principle of, we can use chain rule. Everybody good with this? Okay. So the final element that we've discussed is ReLUs, where the function was that if your input is positive, then the output is the same as the input. So if A is positive, B is equal to A. If A is less than or equal to 0, the output is 0. That's what the rectified linear unit does. So what is the derivative of this sort of piecewise linear function with respect to A? It's just the following quantity. If A is positive, the derivative is 1, otherwise the slope is 0. So based on, if you know, once again, the error at B, you can look at the value of the previous input and decide what the gradient should be. That gets multiplied with that error to compute the error at A. So we've covered all possible cases. One where B was just W times A, one where B was some sum of the previous inputs, one where it was a sigmoid of A, and one where it was ReLU of A. And in each one of those, we have convinced ourselves that if we knew the rate of change of error with respect to B, we can figure out the rate of change of error with respect to A. Or in simpler terms, we can back propagate the error. And we can do this for any branch of the network. And therefore, we can compute the rate of change of error with respect to any weight. Okay? So this is the intuition, not a rigorous mathematical treatment, but an intuition of back propagation, why it works. So why is it useful? Because I would actually start from this. Having decided what my choices for how many neurons I want and which layers I want to be sigmoid and which layers I want to be ReLU, I will connect my network in a fully connected manner. So all possible edges are taken into account. By the way, just want to clarify, in this particular slide, white lines doesn't mean it's +1 weight. I had to just choose some color to draw the network. So here it's just saying this is my starting point, where some random weight is assigned to the white lines. I take an input image, I forward propagate it through the network to compute the error at the final layer, and then I back propagate the error to adjust the weights. And doing so repeatedly, I end up getting a layer, a neural network with some weights are tuned to make this classification based on my training data. So let me show you another representation of the same thing where it will become clear, and then I think because we started late today, we'll probably not be able to cover everything that I wanted to cover. All right, so here's another representation of the neural network. In this case, first of all, I have laid out the network in a different manner, right? It's going from bottom to top, not from left to right. Because in actually many research papers, you will see a vertical stacking of the layers. It's more convenient spatially to draw that. Shouldn't matter, right? So what is this network? It's going from, it has 6 neurons overall. It has an input neuron 1. It has one layer with neurons 2 and 3, another layer with neurons 4 and 5, and then it has an output neuron 6. And then each of them is connected to all possible outputs from the previous layer. This is just, I'm not yet told you how we are tuning stuff. This is just a representation of the architecture of the network. Right, so we have an input layer which will read some input. I don't care if it's pixels or whatever data. Output layer will produce some output. And these intermediate layers are sometimes called hidden layers. I think many of you may already knew that. And here's, by the way, news for you. If you have more than two such layers, it's called a deep neural network, right? So a deep neural network is nothing but it has many, many hidden layers. That's where the deep part comes from. Okay, so this is a plain view of the network, but a better view is the following, actually. And I apologize that the contrast is maybe not so much clear. But what is happening is each of the neurons, you can think of having their own input and output. Okay, so, and in most of the intermediate hidden layers, the relationship between the input and output of that neuron is through some nonlinear function. So let's look at this, right? So what was our input neuron in the toy example? It was simply reading the data. So the absence of no function is the same thing as saying that y1 will be equal to the x of the input. Then what would be the input of the other neuron? It would be the weight W12 times the output of the previous neuron. What would be Y2? It would be X2. F of X2 would be Y2, where F could be sigmoid value, what have you. So on and so forth. Okay? So we know a common function is sigmoid. The other thing we know is at the very top, the output of this entire neural network would be some value which is going to be based on these values of the weights of the network, or some composite function of how the input has propagated through the weights and nonlinearities to the weights, eventually to get to the output. But we already know what's the ground truth or the real value of the input. So we can compute the error at the output as a least square expression shown here. So this is all what we've seen in our example, just in a much more systematic way. So let me just show you the forward and backward passes, and then we are done for the day. So let's say we have some input and the corresponding value of the target or the ground truth. Right? So whatever is blinking corresponds to what I want you to sort of pay attention to. I know the font is pretty small, but let me walk you through what's going on. So if we are given X input, then Y1, or the output of the first neuron, is simply the same as the input, because it's just like a reader. It's not doing any nonlinear function. At the same time, we also know what the ground truth is, which will come into play later once we want to compute the least square error. Then what we do is we look at the output of the input layer, we multiply that by the weight, and that gives me the input of the second neuron. So in general, I can say for all neurons which are the inputs to this neuron, look at the output of the previous value and multiply that with the weights, right? So I know the font is small, but X2 is going to be Y1 times W12, and X3 is going to be Y1 times W13. So very simple algebra so far. What happens next? We are already at the second layer. We know the inputs to the second layer, which are shown in blue rectangles. The output of the second layer is just going to be a nonlinear function of the input. So what I can say is that Y2 is f of x, where f is sigmoid, or f is ReLU, some nonlinear function. And similarly, I think Y3 is going to be f of x3. Good so far? Now we just repeat the entire thing. Now I know what are the Y2 and the Y3 of my network. I want to compute the input of the next layer. And in this case, that would be W24 times Y2, W25 times Y3 for X4, and so on for X5. But it's just a weighted sum of all the previous outputs, where the weights are unknown, remember. So we've already encountered the same thing before. We know the inputs of a neuron. We will just multiply that with f of x. So that will give us Y4 is f of X4, and Y5 is f of X5, sorry. Yeah, I'll let this play out, because I think it walks you through each possible. Right, so we compute Y4. Now we know Y5. It's just f of X5. X6 is just a weighted sum of the y's of the previous layer. And if you know X6, finally you know the output of your neural network, which in this case is just f of X6. And if you know the output, which is f of X6, and you know the ground truth or the target, you can compute the error, which is simply some least square function of the output minus the target. And now you can ask the question that in order to update the weights, I need to compute the rate of change of error with respect to each weight of the of this network. In fact, this is my exact gradient descent update equation, that the new value of some weight ij will be some learning rate alpha, or some value constant alpha, times the gradient of the error with respect to the weight itself. We've seen this before when we studied gradient descent. So the question is, how do you compute this purple quantity for this entire network? And the answer is using backpropagation. So to get the delta error with respect to each weight of this network, shown in this sort of pink box, we also need to compute the rate of change of error with respect to the input and output of each neuron. This is the same thing as saying we are using chain rule. Okay, so we can compute, this was the error, just least square function. So what is the derivative of this error with respect to output y? It's just simply the difference. So we know the derivative of the error with respect to output y. Can we now calculate the derivative of the error with respect to the input of this final neuron? So I want to now calculate what is dE by dx for just this first input. So if my f of x was sigmoid, I can calculate that dE by dx is going to be the derivative of sigmoid times this previous error that I calculated. I see some blank faces, so this is a good opportunity to ask questions if you're lost. If we can calculate the rate of change of error with respect to the output, and we know that for this last neuron, the output was sigmoid of the input, then we can calculate the rate of change of error with respect to the input by using, sigmoid into 1 minus sigmoid. So now we have the rate of change of error with respect to the input of this neuron. Finally, I can calculate these two derivatives, because I know that the input was nothing but weight times the previous output. So the rate of change of error with respect to the weights is going to be the rate of change of the input with respect to the weights, which is nothing but the output of the previous layer. So this is that same as B was W of A, and so error with respect to A is W times error with respect to B. And that allows me to compute that purple derivative. The rest is the same story. I can keep computing all of these derivatives using chain rule. So now this is the same situation as before. For this neuron, I now know what is delta E with respect to, I want to calculate delta E with respect to delta output of this neuron, and that will just be equal to the weight times this previous derivative. The previous derivative we've already calculated before. So it seems like this is a very tedious exercise, but it's actually very straightforward, right? Because you are simply taking products of the error. Because no matter what the nonlinearity or the relationship between input and output was, we always say that the derivative with respect to the input is the derivative with respect to output multiplied by some quantity, where that some quantity depends upon whether it was summation or weight or sigmoid or whatever. But it's always just taking the product of the top level error function. In fact, the way you do this is you don't have to do this every time. Backpropagation is so good because we can, we just simply know what the derivative is beforehand. All we are doing is reading the exact value of that variable in each step. It is not differentiable. Yeah, so that's the reason why we have chosen sigmoid and inverse tangent or ReLU as the functions, because they can be they're either smooth or their derivative is straightforward. Okay, so that's the reason behind those functional choices. So I know this was pretty fast, but part of the reason is because of these technical difficulties. I don't want to necessarily skip too many lectures now. But this was an intuition of how a neural network works. We saw a very toy example of how you can use it to classify a 2x2 image. And intuitively, hopefully, it's clear how the actual process works. In the next lecture, hopefully without any delays, we will learn about really what we want to do, which is the idea of convolution neural networks. So I will show you now what is convolution, why is it different from all of the story that you have learned. And this is what will allow us to build a model that, given some training examples, you can classify. In fact, one of your remaining homeworks is going to be this cross and zero classification using a convolution neural network. So we'll go into much more in depth with that on Thursday. But I think I'm out of time, so I'll stop here.